This talk is about scrambling the superatom universe. So it's basically about fundamental interactions and quantum field theories and quantum entanglement in space-time, chance, Praharas, pan-photonics materials. This is a basic starting slide, just showing something about semiconductors. So these aren't directly going to the topic, but this basically shows some effective mass and band gap and things like that. So they can be used to make devices. We can make certain entanglement devices, quantum entanglement. For example, non-relativistic and relativistic entanglement generation can be done by doing structure design and device design in this material. And if you want to view the universe and its evolution as a superatom, then this is one possible way of doing it at a certain energy range. Obviously, the number of ways, the number of types of cases you can consider is huge. This is just one. I'm starting with it because this is the system I've studied to some extent. And so this can be a part of the superatom time evolution. So here in this slide, we basically shows QCD as an example interaction regime, and you have up quarks and down quarks and strange quarks. So SU3 flavor quarks have coupling to non-abelian gauge SU3 colored gluons, and this basically shows how, for example, up and down quarks can interact by exchanging gluons. So in this talk, we are basically considering the universe as superatom, and then we have quantum measurements, and then you have a certain kind of evolution. We want to study the implications of those, obviously. This is a huge topic and goes into certain arcane mathematical details in many cases. In this topic, we try to keep it more physical in nature, more physics-based. So this can be a part of the superatom universe time evolution. Now, these are just quarks, and there are more types of quarks, and then you have leptons, and you have different kinds of interactions, and you also have the weak interaction, which is mediated by other bosons. Then you have the electromagnetic interaction, and then you have gravity. And gravity is not easy to quantize, but there are certain ways out there, not all of which have been experimentally tested, but there are certain ways. And then you can consider your superatom universe in this context of these, for example, these many fundamental forces or more number of fundamental forces, and then you want to look at this time evolution. We are specifically interested in looking at entanglement structure as it evolves through time. And the entanglement structure is influenced by the measurement sequences that are done in this. So there are sequence of measurements, and then you can have perturbations on those measurements, and then this can lead to scrambled configuration. And so that is the basis for the topic of the talk, which is scrambling the superatom universe. So you can consider more generalizations of the interactions shown in these. You have these force carriers being exchanged by fermions in this case. And you can have other more generalizations where each of these fermions has bosonic partners, and bosons have fermionic partners, and so on and so forth. And we also want to consider the de-Sitter space with gauge interactions along with gravity, and then we want to, for example, here we show up and down quarks and part of the quark sector, and this shows isospin, and then this shows spin for electron and the muon. So this shows some lepton configuration. So these are some of the fundamental particles we know, which we are studying. You can have supergroup, which controls interactions in this quantum field theory, and you can study time evolution. Of course, you need knowledge of states, or at least sectoral parts of knowledge of states, and then this is a time evolution where you have, for example, we have signals traveling at with maximum velocities like velocity, speed of light, and things like that. And the de-Sitter space has metric to determine the interactions of fermions like quark and electron and gas photon interactions. And the SuperAtom universe time evolution is delineated using these frameworks. And the entanglement structure is determined by measurement sequences. And so you can go more into detail about the implications of certain types of quantum field theory for how this evolution can occur and how systems can be segmented and entropy and things like that. But the basic idea is that you can have the SuperAtom universe picture, and it has time evolution, it has measurements, and it has scrambling of configurations related to quantum entanglement. Full de-Sitter space quantum field interactions determine the course of time evolution, and scrambled configurations can result due to measurement sequences in this SuperAtom universe. So we'll stay on this slide a little bit further. So here we show QCD is as a specific kind of complex quantum field theory with complex interactions, because you have 8 kinds of gluons, and you have SU3 color group controlling these interactions, and then you have SU3 flavor, and on top of the quark fermionic flavors, you also have color for the quarks, so the color quantum number comes in. Now, the important thing is these obviously determine the kind of states you can have and the kind of entanglement you can have in a, for example, in a de-Sitter universe, and how it evolves over time. But the fact is we don't know the full extent of how complex the nature of these interactions can be, and how many different kinds of forces are there. So there are more kinds of forces, which with even more complicated interactions may be based on higher gauge groups. For example, it can be SUN, where n is greater than 3, and so on and so forth, and you can have more number of interactions, and those can turn up. For example, there are things like dark matter and dark energy searches, where exotic kinds of particles are always being considered as the possible mechanisms by which dark matter, etc., are generated. And so you can look at this picture as a way to understand how the kind of entanglement you can have in a SuperAtom universe picture, and then you can look at the time evolution. But first you must have to know the underlying quantum field theory in order to do that. So we are in the process of trying to understand through various experiments, and by refining our theories and by comparing theories with experiments about how this is done. But the basic framework for determining the scrambling of entanglement in the superatom universe happens this way. So these are the basic considerations that quantum field interactions determine the course of time evolution, and scrambled configurations can be due to measurement sequences. These are just some other specific material systems that can be used in certain energy and timescale regimes to determine entanglement structures and states. There's some systems I have studied, so I have just some slides about them. Thank you. That's about scrambling the superatom universe.